Excellent. Well, thank you very much for the introduction. My name is Maj Plemenitas, and today I will speak a little bit about the development of generative methods designed for territorial production. So to start off, a little bit of a diagram. Some of these methods are designed to operate on large territorial extents, mainly in the aquatic medium, where we're dealing with islands and coastlines. The approach introduces the in-situ conditions and processes, including forces, materials, terrain, as well as certain ecological factors as vital components in this generative process. They're joined by the strategic multi-scale designed inputs, so-called island nucleation nodes and node networks. And together they start to orchestrate the forces, materials, landforms, and the process of morphogenesis. But before we go into more details, I would like to start with the role of scale and the distinction that this approach introduces. It kind of goes from the standard architectural stance that focuses on what you see is what you get, and expands that scale range quite radically. So we are looking into very small building blocks as well as large systems. In terms of scale, we're focusing on three key categories. One is spatial scale, the other one is temporal, and the third one is the operational. There are a few concepts that are fundamental for this work. They deal with convergent assembly and divergent disassemblies. So these are some of the principles that are kind of inherent to natural systems, where smaller building blocks are starting to build larger operational entities and systems. For the process, we are relying on both digital and physical computation, and understanding that material systems are multi-scalar structures. So to start with the operational scale basically identifies a particular point of view that we want to investigate. It determines our stance. When we speak about the temporal scale, we're oftentimes confronted with two different sides of the coin. One is the acute, that speaks about a certain action, and the other is the kind of long-lasting symptom that results from those processes. All of those are fundamental for the processes that we're investigating, and allow us to create transitions between objects, territories, the ground, and the strata that is resulting from the process reveals particular dynamics of the process. Very interesting diagram here that kind of starts to develop relations between spatial and temporal scales. Those relations between different types of scales are incredibly important as they define intersections. More specifically about the spatial scale, I would like to expose a particular difference that perhaps starts to distinguish the way how we operate in the architectural context and in the context of landscapes. The one on the left kind of implies the architectural logic of assembly, precision, while the one on the right introduces components and constituents that are perhaps found where we don't have direct design control. And as a result, in the way how we organize those constituents, we need to rely on orchestration rather than precise assembly. But both of those have advantages and disadvantages. They have specifics that define their operational logics and their structural capacities. So another thing that is fundamentally important for this methodology is the understanding that resources are finite, and that it is very important to consider the circular aspect and identities of how objects are formed, assembled, and then disassembled into their base constituents. So to kind of move into that initial part of in situ conditions and processes, I'll speak a little bit about the in situ materials, in situ forces, and in situ ecologies as components of the system where we have no or very limited control. However, they are integral, which brings in another interesting condition, that the system is inherently noisy, and we need to identify a level of precision within that noise. This brings me back to the position of scale, the importance of understanding fine granularity. What does it mean to speak about morphology of a particular invisible characteristic of, for example, grain of sand? How that starts to inform processes and patterns across the scale range, both in the lab and on the site. I'll demonstrate that through kind of spatial sequence that explores two different material samples, one on the left and the other one on the right. And as we move through these images taken by a scanning electron microscope, they reveal certain morphological characteristics. And these morphological characteristics that operate on the scale of an individual grain, of course, have consequences that trickle up the system and inform the characteristics of larger territorial morphology. At a certain point, this was a very early study. We started using those characteristics as a way of orchestrating materials and informing their distribution. This was in 2013. And later on, there was a higher level and degree of precision that came into the process. This was largely due to the feedback loops between digital computation, digital simulation and computational simulation, so material simulation and digital simulation that established that critical relation. We were able to achieve a level of predictability in the lab, but also test these concepts on site in several pilot projects in Central America and Pacific. What was interesting is that an idea that started as an abstract idea later on gained a level of resolution, and while we were developing different tools, we were able to approximate those behaviors. This allowed a much faster workflow and process that allowed very clear, very quick iterative development of ideas as well as outputs. We were able to test concepts, test processes, and gain a level of resolution. These processes are primarily operating on a level of a process of erosion, transport, and deposition of granular material. So they combine forces and matter. So I'll go through a few of those just to kind of unveil the resolution in some of this work, as well as the iterative process of selection and optimization of those. So there's an inherent tension between the computational process and the resistance that the material offers in that. but as one develops the structures and exposes them, we also were able to develop them into a multi-scale system, one that kind of operates and acknowledges that, yes, at certain points, we have no direct design control. For example, when we're dealing with the structure of the grain, when we're dealing with the in situ granular material, we have the capacity for selection of a particular site, but again, no direct design agency over the actual matter. When we're dealing with island nucleation nodes, we start to develop direct design control and capacity to simulate those. And later on in the organization, into node formations and networks, we start to develop agency that allows us to translate that inherently noisy process into a predictable outcome. So to structure those strategic inputs into three categories, I can mention them as erosion nodes that locally accelerate the flow and promote local removal of material, sedimentation nodes that increase turbulence and reduce the velocity, therefore triggering the sedimentation of granular matter, and transportation nodes that allow us to transport that suspended medium over larger distances. Of course, we were exploring this primarily initially in the lab through physical simulations and parallel digital simulations to calibrate tools and understand whether there are certain inherent tensions between the two. But it brought us closer into the understanding that, yes, we can understand the individual agency of an introduced object. However, the actual power lies in the combination, how we can accentuate the role of the individual constituent in the systemic way. So these are different formations, combinations of node formations, and the resulting effects on the flow. All of these in combination affect the movement of material and morphological characteristics the end. These processes are not focused only on the surface morphology of the territory, but understand that ground is a structure. So they're highly, they're three-dimensional structures that operate in through time and through the understanding that matter exists on a kind of almost infinite range of scales, but how do we engage with those really affects our capacity to include them in the design process. So these are some of the early morphological experiments that dealt with flow, and that flow started to inform the organization of matter into now not so noisy structures. The role of matter and material is absolutely critical in this process and informs our actions across the scale range. In order to understand that, we worked with embedded and remote sensing, mainly through acoustic sounding, sonars, and other ways of capturing those morphological and structural changes through time. And that allowed us to inform the simulations with more precision and more actual information from the site. So the method allowed production of predictable structures, inherently noisy conditions with minimal input that started orchestrating in situ forces, materials, informing terrain, and designing a generative territorial process. I'll conclude with this. Thank you.